So in this video I'm going to continue with Newton's laws, and remember Newton's laws is for the last couple hundred years before relativity, right? And even now it's the basis of our physics. Most all of our physics is based on Newton's laws. So it's an important concept, so we'll keep doing problems until we feel comfortable doing this. So here is, so imagine we have the following problem. We have a ceiling. We have a string attached to a mass m. Another string attaches to the top of the ceiling. So this mass is suspended by two strings. We're told that the angle theta 1 and we're told of theta 2. We're going to assume that this is a straight line string, very light. Mass is a bit heavy, so it's mass m. And let's make up some numbers. So let's say assume that theta 1 is 30 degrees and theta 2 is equal to 40 degrees. And the mass is, let's say, 20 kilograms. And we're required to find the tension T1. So remember, there's a vector pull on mass m, and there's a vector pull of this string pulling on the mass also. So this is T2. So T1 and T2 are holding this mass suspended in air. And we're required to find T1, the magnitude, and T2. Okay, so our process is exactly the same. You should always remember that we're doing steps as draw a diagram. In fact, usually read a problem and draw this diagram, but I've drawn the diagram first. Once we've drawn the diagram, we should do a free body diagram on all the particles. And once we have done the free body particles, the free body diagram for the particles, then we convert it into a sigma f equals ma, the second law, and maybe we'll have to use a third law, and not in this case because we don't have an interaction between a second particle. But the second law, sigma f equals ma, we substitute everything into component form. Once we get the component form, we get a bunch of equations, solve for the unknowns, and voila, we get what we're looking for. So the process is exactly the same. We're going to repeat this over and over and over again. So it's an important set of steps. It's a mechanical set of steps. So we'll start off again with our free body diagram. So here's our free body diagram. I'm going to label it as FBD, free body diagram. Here is the mass, m, and we can draw this T1 or T2. Here's the T2 vector. So there's T2 force acting on m. There's a T1 force acting on m. So here are the two arrows. And we should put some angles. We know this is theta 1, and so if I know that if I draw it a little more over here, this theta 1 and this theta 1, right, is opposite sides of a crossing triangle. So parallel lines. So this angle and this angle are exactly the same. This angle and this angle are exactly the same. So we can represent this by theta 2 here and theta 1. We also know that beyond these tensions in the rope, right, or string, T1, T2, there's also force of gravity pulling down. So in all of these diagrams, right, eventually you're going to have to make these into component forms. And so I'll actually make decisions on what right and left is. I'll always select the unit vector I to the right, and I'll select the j vector as going up. So in prior videos, I probably selected I to be east and j to be north, but in this case, I'm selecting I to be east, E to the right and j to be up. So minus j is down, minus I is to the left. Okay, so now we have, now that we have a free body diagram, we can now start writing up our next step is we'll have to write sigma f is equal to ma, which is the second law of Newton. So sigma f, so everybody's going to understand this notation, okay? So they're saying the sum of all forces acting on an object is equal to the mass times the acceleration on this object. Now, I have to break these, the next statement is T1 plus T2 is equal to Fg, but I still need to, so I'll write that down. So substituting the three forces in here, T1 plus T2 plus force of gravity is equal to, what's the acceleration of this object? Well, it's stationary, it's not moving, so that must be mass times 0, which is 0. So this is the equation that I'm going to be substituting into. T1 plus T2 plus force of gravity. Now we have to start breaking up things into components, and hopefully I do have enough space in doing this. So let's see if I can do it properly. It's not as if you're in a lecture room, right, where I can just move to another board. But anyway, so here is, let's work with T1. So take a look at T1. Notice that T1, right, is going in the negative to the left, so it's going negative in this direction. And let me erase this slightly so that this directional vectors don't get confused. You don't get confused with the directional vectors. So j is to the i's to the right, j is up. So you're going to draw a little triangle and going to repeat this process again. So remember, the magnitude of T1 is T1, magnitude of T2 is T2. That's our standard notation. So here's T1, and the ratio this side, right, it's going negative, so I know that. I'll put the I first. So T1, this component to this ratio is the, if you think about it, it's the cosine. And so this is T1 cosine theta 1. Notice the minus. T1 cosine of theta 1. And the j component, it's going up. So that'll be T1, and this ratio to this side is sine of theta 1. So this would be T1 sine of theta 1. Okay, great. We now have T1. I'm going to repeat this process for T2. Here's T2 vector. T2 vector is the component of this side to this side, right, is the cosine. So we can write this in terms of the I component, which is T2 cosine of theta 2. I'll put a parentheses in here. And the j component is going up also. So the ratio of this side to this side is T2 sine of theta 2. Now we do the force of gravity. What is the force of gravity? The magnitude of the force of gravity is just the mass times g. We proved it, right? By looking at Galileo and dropping objects in space, right? And we know that the force of gravity is related to the mass times the acceleration that the object feels. So it's ma, which happens to be g. So remember, g is 9.8 meters per second squared, and this approximately across the surface of the Earth. Anyway, so we're going to say this is j, but it's minus mg, where g is 9.8 meters per second squared. So we're going to be working in SI always. So we start substituting this into this equation, which is basically T1 plus T2 plus force of gravity is equal to 0. And start substituting it in. So here's I minus T1 cosine of theta 1 plus j T1 sine of theta 1. Then at T2 is supposed to be I T2 cosine of theta 2 plus j T2 sine of theta 2 plus, and now we have j vector minus mg, and that's equal to 0. Hopefully the 0 got nearly out of board space there. So let's see, there's 0. Yeah, barely. Yeah, I'm making these videos and I can see the monitors to make sure that everything is on the board. Okay, it's on the screen, so it's being recorded. That's good. So next, I'm going to look at the I components. Notice this is the I component. I'm going to pull them together so that we can. So here's the first component, minus T1 cosine of theta 1. Here is plus T2 cosine of theta 2. And that's it. There's no more I components. Now let's do the j components. The j components is T2 cosine of theta 2 plus, oh, I'm sorry, I should be copying this one. I'm wondering why it didn't look right. So let's do that again. So T1 sine of theta 1. And maybe I should have crossed it out so I don't make mistakes like that again. So here's T1 sine of theta 1, okay, And next is the next j component is t2 sine of theta 2 and minus mg, and that's equal to 0. Okay, great. So we've taken this, this, and this out. So we've rewritten it properly into, and I don't know why I'm switching between braces and square brackets, so I'll stick with square brackets right now. So this vector is equal to 0, which means that the individual components are equal to 0. So we now have an equation that says that minus t1 cosine of theta 1 plus t2 cosine of theta 2 is equal to 0. And then we have t1 sine of theta 1 plus t2 sine of theta 2 minus mg is equal to 0. So if you look at the equation, right, we are told the following. We're told theta 1, we're told theta 2, we know m, the mass of the object, and we know g, 9.8 meters per second squared. So we have two equations, and the two unknowns are t1 and t2, exactly what we're trying to find, t1 and t2, and two unknowns. So we have a standard. Now we can actually solve this in a really efficient way by using matrices, but at this point in time, right, I didn't really cover it in this class. But we would actually like to convert this into a matrix form to solve this in a very quick way. But let's do the long way, which is basically solve for an individual variable and back substitute. So I'm going to solve for t2 from the first equation and substitute in the second equation. So let's solve for t2 from with respect to t1. So I'll move t1 to here and then solve for t2 and say that t2 is equal to, so t1 cosine of theta 1 divisible by cosine of theta 2. So we now know what t2 is in terms of t1. Now I'm going to substitute this over to here, and I'm going to do a little bit, I'm going to do a little mental manipulation because I don't think I'm running out of board space. I'm going to start erasing things. I think I'll be erasing this portion, but let's see if I can solve it. So I'm going to move the mg across over to this side, and then this will be replacing t2. And once I have that right, then I'm going to factor out t1. And once I got this factor out t1, I'll have these two terms, and I'll divide. And so I should be able to get the answer as t1 is equal to, let's see if I can do this properly. So substitute this into here for t2, and you shouldn't actually do this, it's just I'm running out of board space and I'm really trying to get the answers down. So you should be going through the steps and not making bad, probably I'm going to probably make a lot of mistakes over here, but maybe not. Let's see. So here's mg, and t2 is cosine theta 1 sine theta 1 over cosine theta 2, so this should be sine of theta 1 plus, then there is a cosine or a sine theta 2 cosine of theta 1, all divisible by cosine of theta 2. Yeah, I think so. And I'm going to multiply cosine theta 2 top and bottom. And so this is now given by, let's see, that would be mg, and then this will be a cosine of theta 2. Mg is cosine of theta 2, and this will be sine of theta 1 cosine of theta 2 plus sine of theta 2 times cosine of theta 1. Great. I think that's about right. Yeah. Okay, great. Now I've solved for t1, and now we can back substitute for t1 to get t2. And I'm out of space, so now, actually, before I continue, now, some of you, right, might recognize that this equation, sine of theta 1 plus cosine of theta 2 plus sine of theta 1 multiplied cosine of theta 2 plus sine of theta 2 cosine of theta 1, right? If you kind of remember your trigonometric angle formulas, right, that's actually the sine of theta 1 plus sine of theta, sine of theta 1 plus theta 2. So it's a double sum angle formula. So, but anyway, let's actually, I don't expect you to know it, but it would be nice if you kind of remembered some of your math trigonometric functions, the double angle formula, for example. But so let's talk about T2. T2 is basically, I'm going to do a, well, actually, T1 is this, and T2 is basically, notice cosine theta 1. If I substitute this for T2, where's T2? Right here. So I've solved for T1. So if I substitute this into T1, you'll notice that T2 is basically the cosine theta cancels. So you're left with, so let me just summarize, and assuming that this is the double angle formula. So just a little side note, I'll put a note over here. Sine of x plus y is equal to sine x cosine y plus sine y cosine x. Hopefully that came up on the screen. Barely. So that came up on the screen. Okay, so that's your sine formula. But if you plug it in, you'll see that T2 is equal to mg. Then we have cosine of theta 1 over sine of theta 1 cosine of theta 2 plus sine of theta 2 cosine of theta 1. And so here's our two formulas. So this is for the tension, in T1 and T2. Now the final step is we're going to substitute these values in to here. So actually, I am a little bit lazy, so let me simplify this into the standard formulas. If you kind of remember this, that these are double angle formulas. So what you're saying is that T1 is really mg cosine of theta 1 over sine of theta 1 plus theta 2. And T2 is equal to mg cosine, oops, did I make a mistake? Yes, I did. That's supposed to be theta 2, the opposite angle. So cosine of theta 1 divisible by sine of theta 1 plus theta 2. Great. Okay. We can try to verify this, but I won't go through the process. I would actually try verification, but it's a little tricky in the math to actually verify these things if you have to double check these equations. Basically, you try to guess the different angles that these equations would make sense in, and try to see if the tensions are make sense. So one way of checking, right, is, for example, if theta 1 and theta 2 are pi over 2 degrees, which is 90 degrees, then T1 and T2 should be going straight up. And so the problem is that, let's see, sine of pi over 2 plus pi over 2 is sine of pi. Sine of pi is minus, is actually 0. So this is 0. Cosine of pi over 2 is 0, so you have a 0 over 0. And you'll have to use your ideas of, so it's a little bit extra calculation to make sure that how do you evaluate when theta 2 and theta 1 are approaching pi over 2. And so you'll have to use the limiting formulas, which I don't think it's just a little more advanced math. But I can do something else. I can find the ratio of T1 to T2, in which case the mg's cancel. It'll be cosine of theta 2 to cosine of theta 1. If it's pi over 2, cosine of theta 2, well, that doesn't make sense either. So I guess I'm going to have to end up like doing formulas like the ratio has two limits approach zero. It's the derivative ratios and L'Hopital's rule and stuff. And I don't think that's a little bit too much advanced mathematics. So let's not assume that. So anyway, this is what we derived, and we should double check and verify. And I can't think of really a simple way of verifying to make sure everything's okay. I guess I could try when theta 1 is equal to like 45 degrees, but anyway, it doesn't really matter. So the last step is in your calculation for T1, you'd actually substitute these numbers in. So the mass would be, what is 30? So this is mass of 20 times 9.8 cosine of 30, sorry, theta 2 is 40 degrees, so put that 40 degrees in, and all divisible by the sine of 30 degrees plus 40 degrees. And whatever that answer is, plug into a calculator. Same thing over here. So mass is 20 kilograms times 9.8 cosine of 30 degrees. I don't know why I put the degrees on the other side, but hopefully you're understanding. Here is sine of 30 degrees plus 40 degrees. Make sure your calculator is on degrees, of course, okay? And whatever numbers you get is the answer in newtons. The answer in newtons. Okay, so this process, right, is kind of very long. And it's a standard process, but you're going to be repeating this over and over and over again. It's a systematic process. You basically draw a diagram, do a free body diagram, I erased it, right? And do a sigma f is equal to ma, and then break up things into components, substitute into our sigma f equals ma, which is here, and then rearrange things until the I and j components, and then get equations and solve for the unknowns. It's a standard set of steps you're going to keep repeating whenever you do anything with Newton's laws.